Good morning, ladies and gentlemen. My name is Efrem Suhir, and we are starting now our long marathon. The course that will be videotaped will last for about 14 hours. And the course is about dynamic response of electronic structures or systems to shocks and vibrations, with the emphasis on the role of predictive modeling. Predictive modeling today includes both computer-aided modeling and old-fashioned analytical/mathematical modeling. In this course, the focus will be on the latter, on the predictive mathematical modeling, because all the, or almost all the, references, the papers that I will be talking about and where the substance of the course is published, the results were obtained by using methods of mathematical physics. But I promise that I will not torture you today and tomorrow in this course with a lot of mathematics. Also, some very modest, moderate mathematics will be there, and I will explain that. But the emphasis of this course will be on the physics of the phenomena. And so that the course, I'll try to make it as palatable as possible for a rather broad audience of engineering students, engineers, scientists, technical managers, for everyone who's in one way or another associated with reliability of electronic and to some extent, much lesser extent, photonic systems and structures. So this short course is, although it is geared towards engineers who work in automotive or vehicular industry, but it's much broader than that because dynamics of a structure, of a system, of a package, of an assembly, and the approaches are pretty much the same, whether it's power electronics, microelectronics, or other areas of electronics or photonics engineering. Now, I will introduce myself, who I am, what I did, what I do. Then I'll go through the fundamentals, basics of dynamics of electronic and photonic systems. I'll go very cursorily over the recently, maybe not even that recently published papers, and then to the great extent possible, detail possible, I describe physics of different phenomena. So I'm Efrem Suhir. I live in this country for about 30 years. For about 20 years, I was with Basic Research Bell Laboratories, Physical Sciences and Engineering Research Division at Mirror Hill, New Jersey. Now I'm on the faculty of University of California, Santa Cruz campus, Department of Electrical Engineering. I'm also a visiting professor with the University of Maryland, Department of Mechanical Engineering, and that actually reflects well what I do. I'm both an electrical and a mechanical engineer. I'm also a material scientist and a physicist. And here you see my telephone numbers, my contact information. And if someone, as a result of this course, will have questions for me, or some comments on my course or critique, or might be willing to get in touch with me, and I will be happy to participate in your projects, your research to the best, and I'll do that to the best of my ability. So a brief summary of my background. I happen to be a fellow of 5 professional societies. Looks like I'm collecting fellowships, but that's certainly not the case, just happened this way, because during my entire professional life, I mind someone else's business, not instead of my own, but in addition to my own. And I started as my bachelor's degree is in mechanical and maritime engineering. That's why when they wrote an article of me in Bell Labs News, the subtitle was "An Engineer Moves from Ships to Chips." For my entire professional life, I dealt with what we can call as reliability engineering. I am a fellow of certainly Institute of Electronics Engineers, IEEE, American Physical Society, and American Society of Mechanical Engineers. Just a couple of years ago, I've been elected to the Institute of Physics UK. And I'm also fellow of the Society of Plastics Engineers because for many years I worked in the area of mechanics of plastics. I'm a member at large with the Board of Governors of the IEEE CPMT Society, Components, Packaging, Manufacturing Technology Society. I'm also a distinguished lecturer with this society. I am chairing a technical committee on portable electronic devices, which is with 2 societies, Vehicular Technology Society and Society of CPMT, Components, Packaging, Manufacturing Technology. For 8 years, I was editor-in-chief, technical editor of the ASME, Society of Mechanical Engineers, Journal of Electronic Packaging. I've authored about 300 publications that include patents. I have about 22 patents, papers, books, chapters, books. Now I'm editor of the book series with Springer on physics, mechanics, design for reliability, and packaging of microelectronic and photonic systems. And I would like to, those who feel that they would like have something to say to the rest of the mankind and would like to write a book or to edit a book, please contact me and we will discuss it, and then I'll bring you to the publishing staff of the Springer. I'm also associate editor of the IEEE CPMT Transactions on Advanced Packaging. Now, just a couple of days ago, I participated in the Board of Governors meeting of this society, and it will be just one journal of CPMT on electronics, microelectronics, packaging, and manufacturing. I believe that will be the title. And I organize many conferences and symposia worldwide. And if you are interested in reliability aspects for different conferences or for some conferences that focus on reliability in electronics, photonics, please contact me and I will inform you on what's happening. I've received a number of awards during my professional life. Primarily, I listed here all the awards that I received during the last 10 years or so. And I am a Fulbright Fellow. I am got an ASME Worcester Reed Warner Medal for outstanding contribution to the permanent literature of engineering, and for laying a foundation of what they say, a new discipline, structural analysis in electronics and photonic systems. In this connection, I would like to say that I happen to be, my accent is a Russian accent, and my PhD degree is from Moscow University, and in this case, Moscow is not Idaho, you know, happens to be another Moscow, which is capital of Russia. And I'm the third Russian American who got this quite a prestigious award, Worcester Reed Warner Medal, for outstanding contribution to the permanent literature of engineering. And my two predecessors were Stephen Tymoshenko, who got it, I believe, in 1925, and Igor Sikorsky, who got it in 1942. I got this award in 2002, I believe, or 2003. So I'm in a good company, and I'm particularly proud of this award. Also, why I want to indicate this award, because my course today will be focused, or will treat electronic systems as structures. And I'll say a couple of words about this approach, the attribute of this approach and this course. And I have also received several other awards from different societies at different times for contributions to the electronic packaging, mechanical behavior of structures. I will just mention the last one here. I was distinguished member of research staff with Bell Labs. In 1996, I got the Bell Laboratories Distinguished Member of Technical Staff Award for developing extremely accurate, as I say, and robust engineering mechanics methods for predicting the reliability, performance, and mechanical behavior of complex structures used in manufacturing of Lucent Technologies product. At that time, Bell Labs was not part of AT&T anymore, but was part of Lucent. Now, as you probably know, Bell Labs, it shrank a lot, and it's part of Lucent Alcatel. The recommended literature, there is abundance of literature of dynamics, shocks, vibrations of structures. And although I'm focusing on, of course, of electronic systems, I want to emphasize to all of you that actually, from as far as dynamics and vibrations and shocks are concerned, it would be very, very useful if some of you also, quote unquote, as I said, mind someone else's business and will have in mind the literature published in many other areas of engineering where people deal with dynamics and shocks. Before I continue and will describe a couple of these 4 items I put here of recommended literature, I want to say the following. The different areas of engineering actually differ by 3 major items. It's different structures, different materials, and different loads, different loading conditions. Structures. In civil engineering in this building, probably it's the structures are plates, different types of beams. This is also true about maritime engineering, avionic engineering, where the structures are plates, shells, beams, rods, you name it. In electronics and photonics, typical structures are composite structures, multi-layer structures, structures built of different dissimilar materials. And as far as materials are concerned, also different areas of engineering are different in terms of materials. For instance, in civil engineering, it could be concrete, could be metal. In maritime engineering, it's certainly metal, very seldom concrete for dry docks or something like that. In avionic engineering, it's certainly high aluminum alloy. So all these materials in different areas of engineering can be characterized by different materials. In electronics and photonics, we probably, these are the areas where we use an abundance of different materials. Even greases, gold, certainly silver, polymeric materials, metals like solders. So probably it's hardly to name any material which is not used in electronics or photonics. And typical structures are multi-layer structures of the type that we used in electronic or photonic packaging. Also, these structures are characterized by significantly different Young's moduli, Poisson's ratio, and so on. In terms of loading conditions, and this brings us to the substance of today's course. The most typical loading conditions in aircraft engineering, let's say, are winds, atmospheric turbulence, gusts. In ocean engineering are waves, and so on. So the loading, civil engineering, probably the same thing, earthquakes in addition to others. But these loading in other areas of engineering, they come, if I can say so, from God. But here in electronics and photonics, these loadings typically usually come, we are the troublemakers. We have to build these structures out of the similar materials, and the most typical loading conditions are certainly thermal loading. And I taught a similar course about a year, maybe a little bit more, a year ago, about thermal stress in electronic equipment. But as far as dynamic loading, recently it has become also an important issue. For many years, people didn't pay attention very much to dynamic loading in electronics and photonics. But for several reasons, and I will describe that in a minute, we consider now dynamic loading as one of the major loading in electronic and photonic systems. And in many cases, although I will not describe that in detail today, we want to consider a situation when an electronic or photonic structure sees a combined action of different types of loading. Could be thermal plus dynamic plus mechanical. Again, also thermal also has to do with what mechanical engineers or physicists deal with. But we typically distinguish between thermal loading, which is due to the change in temperature, and mechanical loading, which is due to the externally applied forces. Now, recommended literature. It's a well-known book, it exists for many years, and here I refer to the second edition of this book, but I believe it had 3 or 4 editions, and the author is Dave Steinberg, and the title of the book is Vibration Analysis for Electronic Equipment. And this is the second edition that I have on my shelf. It's published in 1988. In 1997, I published a book, Applied Probability for Engineers and Scientists, and in this book there is a lot of information about random loading on response of a system, different system, not necessarily electronic, to shocks, vibrations, with the emphasis on random loading. And there are also a lot of examples from electronics and photonics field. I want also to mention the book that was published recently, 2007, in 2 volumes, in which C.P. Wong, Georgia Tech, Y.C. Lee, University of Colorado, and myself, we were co-editors and also wrote several chapters. And the book was published by Springer, 2007, just 2 years ago. And the title is Micro and Optoelectronic Materials as Structures, Physics, Mechanics, Design, Reliability, and Packaging. And there are several chapters in that book devoted to dynamic loading. Now, the last book that will be, here it's indicated 2008, in effect, most likely it will be published in 2010. I will submit this book probably during the next 2, 3, 4 months, where Dave Steinberg, who's a legend in this field, Toxi Yu, who up until recently was chairman of the Mechanical Engineering Department of the Hong Kong University of Science and Technology, and myself, we acted as co-editors, and the book will be published next year. Those who are interested in this book, get back to me and I'll be glad to send you the table of contents. And of course, before it's published, I will not be able to send you out the chapters, but you will see what will be covered by this book. By the time probably this course will probably survive several years, I hope maybe many years. So by the time when you will be using and reusing, rewatching this course, this book will be published. So the cited literature, I'll go very cursorily. You will have all this information on your CD for this course. And I only want to mention that there are many papers that I published, and my course will be primarily based on the papers that I published during my long tenureship with Bell Labs, and during the last several years when I left Bell Labs, retired from Bell Labs, and I'm with these two universities that I mentioned. I will not go through all these papers. It will take too much time, and I would like to rather start presenting the substance, the attributes of the course. But here you see it's quite a long list of cited literature. It's published in reputable, readily available sources. And if for one reason or another you wouldn't be able to find anything, again, get back to me, and I have a lot of information, of course, in my database, and I'll send it to you. Now I will describe the contents of the course. Certainly, introduction. In the introduction, I will describe why we need to know dynamics of electronic and photonic systems. Then I'll say a couple of words, maybe more than a couple, about the role of modeling, analytical and versus numerical, how they interact, how they complement each other. Then I will talk about linear response, and I will emphasize the importance and the attributes about linear response when we can treat a dynamic system, an electronic structure based on linear differential equations, or linear approach with finite element analysis. And this includes what I will be discussing, effect of viscous damping, heavy electronic components subjected to free and forced vibrations. Actually, I want to indicate that as a rule, before you consider forced vibrations, in other words, when you consider an action of a particular load on a structure, you want to understand how this structure will behave after, let's say, after a certain load was applied and that removed. Then the structure will experience free vibrations, and that's important, very important to do as a first step, as prerequisite to the analysis of forced vibrations, because primarily the objective here is to determine the natural frequencies of free vibrations, and coordinate functions, in other words, the modes of vibrations. And quite often, people even restrict their dynamic analysis to the situation when you consider only free vibrations, you determine the frequencies of free vibrations, and then you know the frequency, if it's a harmonic excitation, let's say the frequency of the excitation force. And then if you see that these two frequencies are very far away from each other, in many cases that brings some confidence of the designer that resonant conditions will be avoided. And quite often in practicing engineering, if you avoid resonant conditions in vibrations, you are probably, or most likely, will be in a good shape. That's why the free vibrations are needed not only in order as a first step to understand force vibrations for the given forces, given magnitude, distribution, and so on, but in some cases you can get away with running the free vibrations analysis only. And here I will discuss how these techniques are applied to heavy electronic components mounted on printed circuit boards. In this course, I will not go into the details about random vibrations. It will be too complicated, and you'll have enough headache, enough challenges to understand the physics, and with the situation when you don't have random vibrations but have deterministic vibrations. Nonetheless, I'll say a couple of words about why random vibration modeling and analyses are important, and why and when one should consider uncertainties in what he or she predicts. Then I'll focus on a very important item in electrical engineering, and I ask myself a question, and it's, of course, everything is published. Is the maximum acceleration adequate reliability criterion? We all know, all those who are dynamics, we have a certain number, 500 Gs, 1,000 Gs, and that's the maximum acceleration, and if you're below that, maybe if it's good, if you're above that, it's bad. We want to understand how a system reacts to a certain level of acceleration. The important thing is that from the standpoint of structural reliability, structure quite often reacts, or the criterion should be the maximum stress, not the maximum acceleration. In some cases, in many cases, these two criteria or these two characteristics go together, but there are also cases when if you will evaluate the structural reliability, mechanical reliability, based on the criterion as a maximum acceleration, it will be misled, and I will discuss that. I will not be able to go into the details, and those who are interested can read a paper of mine that was published in ECTC, Electronic Components and Technology Proceedings, and later on I believe it was published also in ASME Journal of Electronic Packaging. Then I will talk about whether shock tests should adequately mimic drop test conditions. It's well known that what triggered the significant interest to shocks and vibrations, in some cases vibrations can substitute, vibration testing can be used to substitute for drop testing or shock testing. But what triggered the interest of this area are cell phones. And you can certainly drop a cell phone, and that will be for a cell phone, it will be the major loading condition, probably not the thermal loading. And there is certainly a temptation and an interest and incentive to substitute drop test conditions with shock conditions because it's easier, much cheaper, easier to measure everything. So the question is, can we do that? The brief answer to this question is yes, we can do that, provided that we know exactly, we model the drop test conditions, and we can tune the shock tester in such a way that it will mimic adequately the drop conditions. I'll discuss that in a little bit greater detail when we will come to these particular things. Then I will focus on a situation when could an impact load of finite duration be substituted with an instantaneous impulse. Why is that important? On one hand, when we model the behavior of a system, it would be much simpler, much easier to deal with an extreme situation when the system is subjected to instantaneous impulse. Of course, real life is not instantaneous, and the actual, even the short-term load has a certain finite duration. But in this case, maybe if we will just model a short-term load of finite duration with an instantaneous impulse, maybe the error will not be that significant, maybe it's acceptable, and it will be very useful. On the other hand, a minute ago I mentioned that there is an incentive and a temptation to substitute the drop tests with shock tests. And in this case, we also want to understand to what extent the short-term loading during the drop testing can be adequately substituted with also a short-term loading of the on the shock tester. At the same time, the existing JEDEC standards prescribe a certain duration. I believe it's 0.1 millisecond of the shock loading, and a certain level of the number of G's of the maximum of the magnitude of this loading. And in this case also, it's important to understand how this requirement is related with the natural vibrations. In this connection, I want to emphasize the following very much fundamental thing. I'll discuss that again maybe a couple of times later on in this course. The course is about dynamic loading. And we heard also, we know also, there is a static loading. What's the difference between the dynamic loading and the static loading? And in order to answer this question, first of all, we should understand that every loading in the world, generally speaking, is dynamic. Static loading is a special case of dynamic loading. What kind of a special case is it? It's a situation when if the duration of the loading exceeds significantly even the lowest exceeds significantly the periods of vibrations. So it's even the lowest period of vibrations is the largest period, and if the duration of loading is significantly longer than that, in this case, the loading can be treated as static. Look at my hands. Let's say that my right hand is a structure, and my left hand mimics a loading conditions. If the structure vibrates with a very high frequency, if the period of loading of vibration is very small and the duration of loading is significant, in this case it's perceived as a static loading. The other extreme is when the period of vibration is very high and the loading is very short. The period is very high, the loading is very short. This extreme case is the situation when we can treat the loading as an instantaneous impulse, and the everything else, the real life, is in between. Therefore, for the two it's always easier to model things when you deal with extreme situations, or typically when you deal with extreme situations, than when you want to address the most general case. And therefore, in one situation when the duration of loading is exceeds significantly the period of vibrations, in this case it's static. If the duration of loading is significantly smaller than shorter than the period of vibrations, it's instantaneous. And here in this paper that I mentioned, that could an impact load of finite duration be substituted with an instantaneous impulse, we want to answer a question: how long is long and how short is short? Then I will describe the situation when we use compliant interfaces. And as we know, in microelectronics and photonics, we often use compliant interfaces primarily because we want to use them as a strain buffer between the similar materials with different coefficients of expansion. But since in the structure we already have a compliant attachment, it might be also we should consider that, and it turns out that it's also very helpful to reduce the adverse consequences of the dynamic loading. And particularly in situations when you have a surface-mounted device mounted on a printed circuit board, and you have a compliant interface, and then you want to understand how it affects the dynamic response. I had a project, still have, a project with IBM, and I mean myself and Milena Vujošević, a PhD specialist in applied mechanics from IBM, we published a paper where we addressed this phenomenon, and I will describe the results here. Then I'll talk about thin and elongated portable devices experiences drop impact applied to its end. That's a very typical situation with cell phones. When you drop a cell phone, you just, it hits a floor. Typically, it's not a flat, blunt impact, but it hits the floor with the edge. And then it can hit the floor either this way, or then after it starts rotating, it will not hit the floor anymore. So it's important to understand what is, first of all, what kind of the impact is more dangerous, whether it's an impact like this or an impact like this. Strange as it may sound, this impact is less dangerous. I mean, will result in lower stresses. Dynamic response will be not as severe as it will be in such a situation, and we will discuss that and why the physics of that in greater details later on. I don't think I published anything, but I'm planning to publish something. I have a project on that with Nokia, and it will be probably a joint publication with Nokia engineers. Then I will talk about experimental evaluation of the effect of the initial position of a portable device on possible damage of its IC as a result of a drop impact. Again, coming back to that situation that I've just described. So if the initial position of a portable device is this, and you drop it, and then it can hit this way or this way. Or the initial position of the device is this, and you drop it, it will hit it this way, and then it will go back again. It can go back either this way, it will be just a single impact, or you hit the floor and it goes back this way, but it will hit the floor again with the other edge. And that's, of course, all these impacts will be transmitted to the printed circuit board, to the solder joint interconnections with all the consequences of that. I will not go into the details. I already explained the physics, but I'll show you some interesting practical results. Then I'll talk about elongated PCB simply because it's simpler, and also because it's the real actual test vehicle, experimental setup that we deal with, I dealt with, has to do with elongated PCB. And then I'll talk about the PCB with a concentrated lump mass at the center. So what people do, because certainly when we run accelerated tests, we want to accelerate the actual situations. You know, as a joke, I'll say that, you know, what is the golden rule of an experiment? Is that the duration of the experiment shouldn't exceed the lifetime of the experimentalist. And that's why we have accelerated tests. We can't wait until things will happen naturally. And because of that, we want to enhance the loading conditions, although in the real life, a printed circuit board will never have a deliberately attached mass to it. But in loading, in experimental evaluations, accelerated test evaluations, quite often in some experiments and practical experiments that we deal with, and by the way, a chapter on that will be published in that book that I mentioned, where I'm editor, and it's a joint publication of this engineer from Intel, Dr. Vujošević, and mine. And this type of tests. And so it's important to understand how the concentrated heavy lump mass attached to the center of the board changes its frequency, its response, particularly not linear response, but so far we are still within the linear approximation. Now, I mentioned just a second ago the word nonlinear response, and in the second part of my course, I will focus on nonlinear response. Nonlinear response for electronic systems is not something which is that we can live without. It's true that in many other areas of engineering, avionics, maritime engineering, aerospace engineering, civil engineering, very often people get away with only linear analysis. Even as I mentioned about half an hour ago that they can often get away with free vibration analysis. This is, in this case, I would say, unfortunately, and the word unfortunately, that's because nonlinear analyses are much more sophisticated and complicated than linear analyses. Unfortunately, we cannot do without these nonlinear analyses in microelectronics, and I have in mind particular situation when we have drop tests or shock tests when we want to adequately mimic the drop tests. Even when we drop a portable device, a cell phone, from a very small height, let's say 20 millimeters, next to nothing, 20 millimeters, that's a little bit less than an inch, on the concrete floor. In this case, it has been established both theoretically by modeling and experimentally that the non-linearity is huge, and I'll talk about that later on in this course, but physically it's due to the fact that the ends of the printed circuit board cannot get closer during the course of vibrations, and because of that, the in-plane, we call the membrane, reactive forces and stresses arise, and therefore the deflection, the displacement will not be proportional to the loading the force anymore. The displacements will be much, much smaller, but the stresses will be due to two types of stresses: bending stresses and the in-plane stresses. And these, the total stresses, can be significantly higher than linear stresses. So we'll talk about the elongated printed circuit board and the role of these reactive, that I mentioned, membrane forces. Then we will discuss the sudden acceleration applied to the printed circuit board support contour. And and I will describe what actually happens, why it happens, and why we have to consider the nonlinear response and how it affects the accelerations. In those cases, accelerations are important, although in this case, accelerations go together with stresses. Accelerations are important for the surface-mounted devices, for their functional performance, while stresses are important from the standpoint of the structural, mechanical reliability of the PCB itself. I'll also talk about the situation when the support contour of the PCB is subjected to repetitive impact loads. In this case, we will compare the linear and nonlinear responses. Then the impact load, we will consider finite but applied to PCB support contour. And also we'll ask ourselves the same question that we asked when we will be describing, or what I described, the contents of the linear part. Could an impact load of finite duration be substituted with an instantaneous impulse? And the answer to this question will be to a great extent different depending on whether it's a linear response or a nonlinear response. In other words, depending on whether it will be a relatively small amplitudes, whether linear response is applicable, or it will be relatively large amplitudes and large membrane forces. And the answer to this question will be to a great extent different, and we will discuss that. And also I want to emphasize right from the very beginning that in order to give the right answer to this question, you have to do the modeling of that type that will be described in this course, or, well, has been described in the published paper. And also I'll talk about the role of the coordinate function. You remember at the very beginning, it's about a half an hour ago of this course, I said that in free vibrations,